So we've now gotten practice with drawing some covalent molecules where we have atoms sharing their valence electrons rather than doing a give and take. So the whole shebang is neutrally charged. There's no cations or anions, and everything sticks together through that mutual benefit of co-ownership over some electrons. Okay, but so far we've just dealt with some easy examples of making diatomic molecules where we just put two atoms of the same element together. Okay, we're going to step it up a little bit this time. So these instructions are actually from the last assignment. I forgot to change them. Okay, and we're going to draw some tougher Lewis structures, which is what we call those drawings with the lines and the dots. Okay, for molecules that contain atoms of different elements, so they're covalent compounds. Okay, and might also be more than just two atoms, which can make it a little bit trickier too. So we'll talk about how you can kind of figure out how to draw these. So first up, we're going to do a molecule of HI. Okay, so this formula tells us that we've got an atom of H. We've got an atom of iodine, I. Okay, hydrogen only has one valence electron, so I'm just going to give it one dot. Okay, and this is a trick you kind of pick up the further you get into these. I know that in order to make a covalent molecule out of this, these guys are going to have to bond. Okay, there's going to have to be a connection. There's going to have to be a line between these. So when I draw the valence electrons for iodine, I'm going to go ahead and make sure there's one lined right up to make that bond there. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, so I've got 7 valence electrons around iodine. If you want to clean this up, a lot of times we'll throw the electrons that aren't bonding out of the way of the bond. So I might scooch this one over here just to clean it up a little bit. Doesn't change a whole lot. Doesn't change whether your answer is right or wrong in my eyes, but might make it look a little bit nicer. And it might fit something you might see in a textbook or online or something like that. Okay, so I've got to have at least one covalent bond to make these guys happy, to make them a molecule. So let's connect these here. All right, and I'm going to get rid of the dots so I don't confuse them or double count them. So now my hydrogen atom has its 2 valence electrons to fit that duet rule to kind of have helium's electron configuration. Iodine has an octet with its original 7, and then another one from the bond. And so everything ends up happy here. So this looks like a good molecule of HI that is more stable than those atoms alone. Just as a note, those circles that I draw around these guys are not really part of the structure. It's just to kind of help keep track and show how many electrons we have total after we do all the bonding and stuff. So I'm going to start leaving those off on these drawings, kind of on the final product. Okay, let's try a tougher one. Draw a molecule of SCl2. Okay, well, we've got 3 atoms in this one. I've got an S and I've got 2 Cl's. So how do I figure out what goes where? Is it going to be like an S and a Cl and then a Cl, or is it going to be like a Cl and then an S and then a Cl, or are they going to be like in a triangle of like SCl, Cl like that, or So here's how we're going to approach problems like these. We're going to assume that one atom is in the center and everything else bonds to that one atom. Okay, now how do we pick that one center atom for everything else to bond to? Well, there's a couple ways, and one way is to just look for the odd thing out. Okay, in this case, we have one sulfur atom, one S, and we've got 2 chlorine atoms. So out of these options, our sulfur is probably the best bet to put in the middle here. So I'm just going to put my sulfur smack dab in the middle of what this molecule is going to be. All right. And I'm going to try and bond this to 2 chlorine atoms. So I'm going to kind of spread them out and give them some room. So I'm going to put a Cl there. And again, I'm not going to I'm just going to put this one over next to this. These guys have electron clouds. Okay, and they need space. Electrons repel each other. So if I try and just like say, oh, I'm going to put a Cl right in there next to each other, these guys are going to kind of fight and clash and push away from each other. So to make this happy, and that's all really want for these guys is for them to be happy, right? I want to put them as far apart from each other as I can. I want to give them that space that they deserve. So if these are both going to be bonding to this central sulfur atom, I'm going to try and space them out on opposite sides. They've got plenty of space in between them, okay? And a lot of times this ends up looking kind of symmetrical in your drawing, if that helps. Okay, now sulfur has 6 valence electrons. So I'm going to put a dot here and a dot here because I know that's where I'm going to be making some bonds to these chlorine atoms. I'm going to put the rest kind of off on the sides. 1, 2, 3, 4, plus the 5, 6 there. That looks good. My chlorines have to bond to the sulfur in order for this to be a molecule. So I'm going to put those electrons there and then give them the rest of their 7. So that's 1, 2, 3, 4, 5, 6, 7. This is 1, 2, 3, 4, 5, 6, 7. All right. And I've got to make them bond at least once each to this sulfur atom here, or else it's not a molecule. So let's make a bond here, make a bond here. Okay. For posterity, I'm going to erase the dots at the ends, so I'm not double counting electrons. Keep erasing the bond. It's okay. So each of those lines represents that pair of 2 electrons. Each chlorine winds up with 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So that's happy. That's stable. And our sulfur is going to wind up with its original 1, 2, 3, 4, 5, 6 plus 7 from this bond and 8 from that bond. It also has an octet, so it's ready to go. This other chlorine is just the same as this chlorine. It's also going to have its original 7 plus 1 more from that bond. So this way, everything is happening. It all works out pretty darn well this way. Okay, so look for an odd atom out to stick in the middle. Let's do another example. Draw a molecule of CO2. We're doing carbon dioxide. Okay. So again, if I want to know somewhere to start, I'm going to need at least one atom in the center to bond everything to. And out of these options, I've got 1C and I've got 2 O's. My 1C is probably my best bet here. Okay. So let's draw that out. I'm going to put my C right here. I want to spread out my oxygen atoms kind of far away from each other, but they still have to be able to bond with that center atom, so I'm not going to put them out too far away. So let's put an oxygen here. Let's put an oxygen here. All right. I'm going to give them their respective number of valence electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and carbon's going to have 4 valence electrons. 1, 2, 3, 4. And I'm going to try and leave at least one that's already kind of lined up so that I don't have to clean up my structure too bad afterwards. Okay, so in order for this to become a molecule, these all have to be connected by a covalent bond there and there. Okay, which is looking okay. All right, but let's see. Our oxygen is going to have 1, 2, 3, 4, 5, 6, 7 valence electrons so far. Not quite there. Same thing with this guy here. And our carbon has its original 1, 2, 3, 4 plus 5, 6. It is still a little ways away from having an octet. So we need to do some more work on this. If you remember the O2 example we did before where we had diatomic oxygen, just 2 oxygen atoms bonded together, one single bond wasn't enough. So maybe we need to do a double bond here. So it's going to be a little messy, but let's just try this. So if I had another bond here, that would give this oxygen atom 1, 2, 3, 4, 5, 6, 7, 8 ownership over 8 electrons. in the valence energy level, so an octet. That's good. And our carbon's now up to 1, 2, 3, 4, 5, 6, 7. Cool. It's closer, but not quite there. Maybe we make this oxygen happy by making another covalent bond. This will solve the problem. So this oxygen goes from also 1, 2, 3, 4, 5, 6 to 7, 8. And then our carbon should now have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons as well. Everything's happy. So it just took 2 double bonds to each oxygen. We got a double bond, we got a double bond on either side. So now we can kind of clean this up a little bit. So let me redraw this. So I'm going to put these valence electrons kind of out of the way. Put these ones kind of lined up to make that double bond. Get 2 here, get 2 here. So line those up for a double bond. And then connect them together. So that looks much better. Okay, so this is our molecule of CO2. C is the odd one out, it stands in the center, and it double bonds to each oxygen to get everything to an octet, to get everything more stable. Okay. Let's go for another example. Draw a molecule of COCl2, okay? And this is an L. It's part of chlorine. It's not Ci2. That sometimes catches people and confuses them. Okay, well, we have 2 things here that could be kind of considered on their own, kind of the odd one out. We've got a carbon, and we've got an oxygen. Okay, now there are a couple ways we can try and figure out which of these odd ones out we can use for our center atom. One good way is to figure out which one is less electronegative and is therefore more willing to share its electrons with other things. So if I go and compare carbon and oxygen, let's see, the most electronegative stuff on the periodic table is in the top right of the periodic table. So oxygen is closer to that corner, so it is going to be more electronegative. It's going to be greedier with its electrons, and therefore, if it doesn't have to share as much or give as much, then it won't. Carbon, on the other hand, is a little more willing. It's a little more giving. So it's okay with making bonds to share, with a lot of stuff, like how we had, carbon making a total of 4 bonds up here for carbon dioxide. So I would say carbon's probably the best option to put in the middle. It's going to be the most willing to bond to everything. And again, we just want one center atom for everything to bond to. So let's try it. I'm going to put carbon in the middle here. We'll put oxygen on the top and chlorine on these sides. And again, I'm going to try and spread it out. And since I've got 3 things, 2 chlorines and an oxygen, I'm going to make kind of a triangle out of these to give them all sort of this even amount of space in between each other. Okay, and of course you don't have to do it like this. You could do the Cl up here and there, or you could do it, there and there, however, which way, doesn't really matter. But this is just kind of the way I chose to do it. Okay, now again, kind of to shortcut this, I know I'm going to need everything to bond to this carbon at least once. So let's put an electron. Oh, come on. Oh no, my pen's not working. There we go, it's back. Okay, so I'm going to do kind of show an electron on each of these kind of lined up and ready to go on each of these. Okay, let's see. Carbon should have a total of 4 valence electrons. So I'm just going to kind of leave this last one sort of down here for now. Okay, each chlorine should have 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And then oxygen should have 6. So 1, 2, 3, 4, 5, 6. That should be good. Okay, let's try and bond these and see what works. So I'm going to make a covalent bond from my chlorine to my carbon, from my chlorine to my carbon. Okay, that gets my chlorines from 7 valence electrons to 8 octet. Great, my chlorines are done. So I don't have to touch those anymore. My carbon goes from having 4 valence electrons to 6 from these 2 single bonds it's now participating in. So I still need 2 more valence electrons. Okay, I've got to bond to this oxygen to make this work. Let's see. Well, that puts the oxygen from 6 valence electrons to 7, and my carbon is going from 6 to 7 also. So if I want them both in an octet, it looks like I'm going to need a double bond. So I'm going to rearrange some of these electrons so that they're kind of, again, in the line of doing this. So let me scooch this one up here. Let me scooch this one down here. So they're all lined up and ready to go to make a double bond like that. So my carbon is now at 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Oxygen's at 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So carbon's good. Oxygen's good. This looks like a pretty good Lewis structure for this molecule COCl2. Okay. And remember, you can always draw a messy version first and clean it up later. Okay? If you're doing something like this and you end up with your stuff kind of like this, and you're like, ooh, that could be spread out more. Maybe I could kind of like put this guy a little bit more over this way, or something like that. Don't be afraid to redraw your structures. Once you've got it figured out to get everything the octet, and you got everything stable, then you can make it all nice and clean. And the more you practice it, the better you get at just being able to do it off the cuff. Okay. So we got some other examples that involve more atoms, like this NClO has N, NCl, and O. So we've really got to pick an odd one out from those. And again, remember, you're looking for the least electronegative thing, the thing that's going to be most likely to kind of bond with the other stuff. It can also be a good sign to see how many bonds something can make. So if nitrogen starts with 5 valence electrons, it could make 3 covalent bonds total to other stuff. So it's most likely to be in the center if the other guys, like the O, can only make 2 covalent bonds before they're full, or chlorine can only make 1 covalent bond before they're full. That can also be kind of a good tip-off for that. It doesn't work every time, but it works quite a bit. Okay, got PF3, CS2, PF5, and XE4. So this last example I'm going to do, PF5, is going to be a little interesting. So P, phosphorus, is going to be our standout. Let's put it in the middle. Fluorine is going to be around the outside. Let me just try and space them out. Fluorine, 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 fluorine. Okay, and each of these fluorines should start with 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 5, 6, 7. Okay, I'm going to erase this so it doesn't get in the way. Okay, I know phosphorus has to bond to all of these at least once. Okay, if you remember doing the diatomics, fluorine was one of them. You might look at this and be like, ooh, I can make fluorine bond to fluorine, and then those guys are happy and I leave them alone. But this PF5, this formula tells us that all of these are bonded together. So everything's got to be bonded to this central phosphorus atom. Phosphorus, like nitrogen, has 5 valence electrons. I know they're all going to have to bond, so I'm going to kind of try and line these up with the fluorines. Let's draw some covalent bonds. There, and there, and there. That was kind of messy. And there, and there. Okay, so each fluorine goes from having 7 valence electrons to 8, which is great. Haha. But something weird has happened with our phosphorus. We are now at a total of 10 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since each of these covalent bonds is a pair of electrons. So we've passed the octet. So this is why it's kind of it looks nice to be able to be like, ooh, if I've got too many electrons, maybe I just make the fluorines go and bond by themselves and they aren't a part of this. But that's a different compound. This is telling us we have to have 5 phosphorus atoms all bonded to, or sorry, 5 fluorine atoms all bonded to this phosphorus. So this must be how it is, but it doesn't seem right because we're breaking the octet rule. We have more than 8 valence electrons. If something doesn't seem right about your structure, and your gut's telling you there are not enough valence electrons or there are too many, then we have kind of a surefire way to get a structure to work out. I have the steps kind of linked in a separate PDF, but in short, this is what we're going to do. First off, we are going to put the least electronegative atom in the center, just like usual, with the other atoms kind of evenly spaced around it. So that much hasn't changed. It's fluorine, 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 fluorine. Okay, but rather than giving everything the usual number of valence electrons, we're instead going to kind of pool them all together as if we've got like a shared set of resources for all these atoms. So let's see, we've got each fluorine with 7 valence electrons, and we have 5 of them. 7 times 5 gives us 35 electrons, kind of pooled in from fluorine. And phosphorus gives 5 electrons. So we have a total of 40 electrons to spend to make this molecule happy. And we've got to use all 40, no less, no more. They got to be somewhere. Okay, so I've got to use 40 electrons here to make this phosphorus with 5 fluorines, this phosphorus pentafluoride, happy. Well, I know everything has to be bonded together. So let's make our bonds first. 1, 2, 3, 4, 5. I've made 5 covalent bonds to get everything to stick together. This is kind of the bare minimum of what the molecule needs. So since each bond is a pair of electrons, I've now spent 10 electrons. I'm down to 30. Okay. Now, I'm going to next try and get all my fluorine atoms on the outside happy. I'm going to try and get them to an octet. Okay, since these guys are more electronegative typically, we need to kind of make sure they're satisfied first because they're really greedy for their electrons. So each of these fluorines has 1 covalent bond so far, which means they have ownership over 2 valence electrons. So to get to 8, each one needs 6. 1, 2, 3, 4, 5, 6, plus the 2 from the covalent bond makes 8. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I kind of got it obscured there. 5, 6. Okay. Since I put 6 electrons on each of these 5 fluorines, I'm now down to, well, 0 electrons. I've run out. Okay. So if I had any extras, I would put them on this center phosphorus atom, or whatever your center is for your molecule, and say, well, I've made everything else happy, so now it's time to throw the rest onto my center atom. From there, if you still don't have an octet for anything, you can start making double and triple bonds, not by sharing 1 electron to another, but just by giving a pair of electrons over from the surrounding atoms to the center atoms, which is a little bit odd. Okay. So again, this list of steps is kind of separate, and it's a little bit exhaustive to draw a molecule, which is why I like to teach it kind of by the gut method first. We try and just get the valence electrons to work out by making covalent bonds that make everything happy. But this can be a nice little backup if you are kind of up against a wall and you're like, oh, I don't know what's going on here. Like, for instance, in number 10, when you try and make this molecule, xenon is a noble gas. It already starts with 8 valence electrons usually. So, like, what? Hey, usually we wouldn't want to make any bonds, period. Most of the noble gases don't do anything exciting like bonding with other stuff because they already have an octet. But in this case, xenon is going to end up with more than an octet as it bonds to 4 fluorine atoms, which is kind of crazy. Okay, so use that set of steps as a backup. Okay, put your least electronegative atom in the middle with everything else surrounding it, and use that pool of electrons to kind of throw on to the surrounding atoms first, then the center atom. And if things still aren't happy, that's when we can resort to double and triple bonds by giving them just a whole pair of electrons is given to make the bond from the surrounding atoms to the center atom.